So let's start 10th week discussion on the Galois theory course. So if you have your doubts, you can ask in the comment section. Okay, so okay, so we'll start with problem number 1 in the exercise without discussing what is done in the class lectures. Okay, I hope you are going through the lectures. Okay, so this is first question where we have pi, which is rational polynomial, which is irreducible polynomial with rational coefficients of odd degree and degree bigger than equal to, sorry, is strictly bigger than 1, with only one real root, with only one real zero, so that the field extension Qx is not normal. Okay, so what are all the what is the definition of normal extension? If Okay, let me change the color first. If fx belongs to qx such that f of alpha is equal to 0 for some alpha inside qx, then f splits into linear function. Or this is when if qx over q is normal. The same thing is the same thing, or equivalently, if any irreducible polynomial, any, okay, here it was needed it irreducible. If f irreducible, any irreducible polynomial f in Qx has 1 0 in Qx, then it has all the 0. Okay, so this is definition of normal field extensions. Okay, so we are coming to our claim that Qx over Q is not normal, because when f is irreducible of odd degree and only x belonging to R is 0 of f, or let me write real 0 of f is real 0. Real 0 means 0 in real numbers, okay, is only 0, and other and all other 0 roots are complex. Then since qx is contained in real numbers, right? Because since x is contained in real numbers and real numbers is a field, and qx is the smallest field which contains x and q. So, and other roots, let uh, x1 is equal to x, this collection, and x2, x3, xn, this is let's say v, f, c, then v, c, f minus x. This set is not belonging to qx because these are complex numbers, right? Complex roots. So f has not all roots inside qx. Okay, so this was even general for any field extension L over K, and f belonging to Kx, which is irreducible, and f of alpha is equal to 0 for some alpha belonging to L. Then f splits into linear factors in L, or equivalently, any reducible polynomial f belonging to Kx f has 1 0, and let me write like this, and f has 1 0 in L, right? Then it has all the zeros of f inside L. Okay, so this was definition for normal extensions. We have shown that qx over q is not normal because the other zeros of the polynomial pi. Okay, here everywhere it was pi. Okay, qx over q is not normal. This is when pi. Okay, pi is irreducible of what degree? Bigger than, is strictly bigger than 1. There are some complex numbers, like this is non-empty set. this cardinality of VCF is bigger than or equal to 2. Okay. So in that case, this set is non-empty and it is not inside QX. Okay, so I hope everything is clear up till here. So I can go to next question. Okay. So in the next question, what we have and that pi be an irreducible polynomial of degree n. Yeah, pi be an irreducible polynomial of degree n, and let L over K be the field extension, a field extension of degree m, and the CD, if they are co-prime, then that the CD is 1, then pi is also irreducible in LX. Okay. I hope screen is getting recorded. Okay, so let me start about this. We have this extension L over K of degree m, and we have irreducible polynomial of degree n. Then this extension K x modulo pi, because f is irreducible, this is a field. I'm writing it as K small x. Okay, this field extension is of degree because this is simple extension, so its minimal polynomial is just pi. This x has minimal polynomial just pi. So this is of degree n. Sorry. Okay, so attaching this element x to L, what we'll get? Lx. So if you see here, x is an element. Okay, x is an element in Lx, and x satisfies some n degree polynomial pi here, right? Okay, these are not arrow, but they are field extensions. Okay, so I'm writing like this because they are injective map of fields. Okay, and k small x is contained in here, Lx. Now x belongs to Lx, and we have these two pi x is equal to 0. This is clear because uh, x is x is and pi is nothing but mu xk. This part is clear. Now pi belongs to Lx, since pi belongs to kx, or let me write stepwise. Since pi belongs to kx and k is contained in L, so it also belongs to Lx. And now in this extension, this part, X satisfies some, let mu be polynomial. What should I write? Let me change the color. Okay. Let this is mu x L be minimal polynomial which is irreducible by default. Minimal means monic and irreducible polynomial which satisfies x. Be the minimal polynomial in Lx such that mu xl of x, this is it. Minimal polynomial by definition it is satisfying x. Okay, so minimal polynomial in Lx, minimal polynomial of x. Okay, minimal in this sense, minimal and satisfying x. Okay, this is minimal polynomial of x, and pi x is equal to 0 and pi also belongs to Lx. All this together implies mu x L divides pi, because mu x is smallest degree polynomial in Lx. This is minimal polynomial. Okay, so which satisfies x, and pi should be some multiple of mu xl. Okay, so I hope this is clear up to now. Now what we want to use GCD of m and n is equal to 1. Okay, so let's see. Ah, so here we want to write degree of extensions in this diagram. Okay, so let me write it again. L over k, kx here, lx here. Then in this diagram, or that is degree of extension lx over k, what it is. This can be written as in two ways, right? One is this Lx over L, this degree, into L over K, this degree. And same in this direction, you can write is Lx over Kx into Kx over K. So here we are given this is n degree extension and this is m degree extension. So we can replace this condition. What we get? So Lx over L, we have to write just like that. Lx over L, and then L over K. I'm writing this. L over K is just M. So into M is equal to this side we have Lx over Kx, just like we just write like that. And in this part Kx over K, we have this degree N. Now because M and N are, since this GCD M N is 1, what we will have n should divide Lx over L, and m should divide Lx over Kx. N divides Lx over, okay, degree of extension, yeah, Nx Lx over L. And what is this? Okay, let me write in next line. But this is simple extension Lx over L. So what is this? Lx over L degree. Lx over L. This is nothing but degree of the polynomial mu xl, right? Okay, so what should be our next line of argument? Uh, this is just degree of mu xl and n divides that. So n should be even these two lines should imply that n is in fact smaller than or equal to degree of mu xl. And let me denote it as second equation, and this part first equation. What we have, mu xl divides pi is of degree n, right? So what we get from from star and bus star, both are for degree same. Degree of mu xl is same as degree of y, right? So what first star implies? This implies degree of mu xl is less than or equal to degree of pi, which is equal to n. But this double star implies is written here, right? So both degree are same and equal to n. Okay, so let me delete. Now, pi and mu xl is irreducible polynomial, and pi, this will imply mu xl divides pi also, and both are of degree same. So both are monic, as pi was already monic. We could have taken that. This implies mu xl is same as pi in Lx. This implies pi is irreducible. Okay, so because mu xl is irreducible, and we have shown that mu xl is by default irreducible. It is a minimal polynomial. We are choosing irreducible. So now pi is equal to irreducible polynomial, and pi is also irreducible. We are showing like that. Okay. So I hope you understood this part. Now let's see next question. Here we have L finite field extension, where x1, x2, xn are these are algebraic sets, sorry, algebraic elements over K. So that L over K is normal if and only if L is a splitting field of mu. where mu is, this is by definition, mu x ik is minimal polynomial of xi in kx. Okay, so this was definition. Okay, I'm using again and again, so remember this. So we will show which part should be easier. L lowercase normal, then L is a splitting field of L is k x1 x2 xn over k. If it is normal, if L lowercase normal, then L is a splitting field of mu. Mu is this polynomial. So first of all, yeah, this part is easier. So I'm proving this part. Okay, assume that L over K, this is normal extension, normal field extension. Okay, if it is normal, then mu is some polynomial, right? Okay, and note that mu belongs to kx, which is mu belongs to kx. In fact, I should write mu xi, or no need to write that. Let me write from here. Mu xi k are irreducible polynomial. Let me write for every I. Okay, this is irreducible polynomial in kx such that xi belonging to L are okay for every I. Let me write this is somehow wrong. Mu xi is I should use, and xi a root of mu xik. Okay, for every I this is true. This implies for every I, okay, whatever I belonging, I is running over 1 to n. Okay, that's all. For every I, mu xi is a irreducible polynomial and it has some root of, so for every I, zero set all the zeros of all the zeros of mu xi k belongs to L, right? Because mu xi has one root inside L which is just xi. So all the zeros of mu xi should belong to L because L is normal extension by definition. This implies uh, all the zeros of mu, which is product of mu xi, belongs to L. In fact, this is the V of mu. This is nothing but union of V of VL, mu xik. Okay, I from 1 to n. So union of sets inside L is again set inside L, some set. Okay, so this part is clear. Okay, now all the zeros. Okay, this is clear that all the zeros of mu are inside L. So splitting field of mu, let L prime be the splitting field of mu, then L prime, all the roots attached is equal to k VL mu. Okay, we are just attaching all the roots of mu into k. This is our splitting field of mu, and this is nothing but we should write all the roots of mu xi VL, this union VL mu xi k, I from 1 to k. All the roots of mu xi we are attaching. Now this is equal to just k x1 x2 xn. This is this part. So and now okay, this is our question mark for time being. How we should show, since this VL mu, this is subset of L, this implies L prime is contained in L. Okay. On the other hand, since x1 xi belongs to L prime, right? Xi belongs to this zero set inside. This implies k x1 x2 and so on xn. This is contained in L prime. This implies L is contained in L prime. So that's how we have shown that L prime is equal to L and is a splitting field of mu. Okay, this part was easy. Now on the other hand, we will show that L over K is normal, and assuming that L is split, assume L is a splitting field of mu. Okay, mu is by default, by definition, it is mu xi k, I from 1 to k. 1 to n, it is given L over K, and L is just, we are attaching n elements, x, y, x I am just writing. Okay, I from 1 to n. It is given, and we want to show that L is normal extension. L is L over K is normal. So let us start with some polynomial, irreducible polynomial f, and 1 0 which lies inside L, and we'll show all the zeros of f, they will lie inside L. Okay, then L over K will be normal. So I'm starting proof here. Okay. Let f belongs to kx be irreducible polynomial, and alpha inside L be a root of f in L, will show f splits into linear factor, or f has all the zeros inside L. So this is our claim. We will show all the roots of f belongs to belongs to L, or equivalently f splits into linear factors inside L, inside Lx. Okay, so for that what we should do, we have this alpha inside L which is a root of f. Now consider, let beta be any other root of f. First of all, consider this field extension. Consider a field extension which is bigger than L. In fact, consider E over L field extension such that f splits into linear factors inside Ex. In then we'll show that all the zeros, they belongs to L. Okay, we'll show that this. Now let alpha alpha is already in L, so let beta, which is not equal to alpha, be a root of f. We'll show that beta belongs to in E. We'll show claim is that claim beta belongs to L. Okay, this is our new claim. Then all the roots of f which are in E, by the same proof, all the beta, all the roots of f, they will be inside L, and the proof is done. Okay, so beta is not equal to alpha. We can take this extension, field extension, in such a way that E becomes Galois extension over K. Is this possible? Or E containing, so okay, let me rephrase it. What I'm doing, E is extension over L, L is extension over K, such that all the roots of F belongs to E. So now, what about this automorphism group of E over K? K algebra automorphisms of E. Okay. Let So first of all, because F is irreducible, since F is irreducible, then since F is irreducible, what we have, zeros of F, sigma belonging to automorphism group, K algebra automorphism of E permutes the roots of F, right? Permutes the roots. Okay, so there will be an automorphism of E, where sigma will send alpha to beta. Okay, roots of, so this is true for any sigma. So there is a K algebra automorphism of E such that sigma of alpha will be beta. Okay, but what is sigma of alpha? First of all, what is alpha? Alpha belongs to L, and L is of this form: K x1 x2 xn. So alpha looks like some px, px1 xn is some polynomial in x1 x2 xn, q divided by some polynomial in x1 x2 xn, which are mutually co-prime, and of course q is not zero. Okay, so alpha is of this form. Now if you apply sigma to alpha, and sigma is K algebra automorphism, Okay, I will write it. Sigma of alpha will be sigma of p x1 x2 xn by q1 q x1 x2 xn. But this will be k algebra automorphism. So sigma will go to sigma will go inside, and what it will become? Yeah, first of all, any this can be written as r x1 x2 xn. Okay, some polynomial. Why this is true? Because when x is algebraic, when x is algebraic over k, then k round bracket or square bracket, they're same, right? So in particular here, k x1 x2 xn round bracket is same as k square bracket of x1 x2 xn. So any element can be written as a polynomial also. So r, this can be written as sigma of r x1 x2 xn, some polynomial r. Okay, this implies, because sigma is in k algebra automorphism, this will be same as r of sigma x1 sigma x2 sigma xn, right? Now sigma of xn, sigma of each xi, okay, I'm writing this is equal to, I'm just calculating what is beta. Okay, beta is equal to r of sigma x1 sigma x2 and so on sigma xn. Mu xi is irreducible polynomial, so sigma xi is sigma xi. This is a root of, till now we have not used Alice splitting field of mu xi. So all the roots of mu, hence mu xi, they are inside. Okay, I should write that part. Since L over K is splitting field of mu, L contains all the roots. L contains all the roots of mu. In particular, all the roots of mu I, mu xi. So, and sigma is okay. Now mu xi k is irreducible and xi is one of the root. So sigma xi is also a root of irreducible in kx and sigma is k algebra term. Okay. Uh, okay, one minute. Mu xi is irreducible in kx and sigma is a k algebra automorphism of E. So sigma xi should be also root of mu xik. Now, since all the roots of mu xik are in L, so these elements sigma xi belongs to L for every I, and R is a k polynomial. R coefficients, R has coefficient from k. Hence, hence this R sigma x1 sigma xn, this belongs to k L. Because L is already in k, so this belongs to L, and this was just beta. So this is how we shown that beta belongs to L. Okay, hence L over k is normal. So I hope you understood. If you don't understand, you can again go through it. Okay, so let me see next question. Okay, so pi is again a reducible polynomial over k. L over k is normal field extension. Then G and H be. So then the questions are G and H be irreducible polynomial. Sorry, irreducible factors of pi in Lx, so that there exists sigma inside automorphism of L over k, thus that sigma of S is equal to G. So I will be back in few minutes. Few seconds. Okay, let me come. I'm going to drink water. Yeah, let me start this again. Let pi be a reducible polynomial over K and L over K be field extension or normal field extension. And the first question says that if G and H are irreducible factors of pi in Lx, so that there exists some sigma, which is an automorphism of L, algebra automorphism, then which satisfies that sigma of H is equal to G. Okay, so here we have K or L is field extension, but else we know this is normal field extension. And pi is in Kx, which is irreducible. Polynomial such that pi is equal to f into g, sorry, g into h, where g and h are irreducible polynomial in Lx. Okay. Okay, so now we have to show that sigma of s is equal to g or some sigma. Okay. Now for this, let E containing L containing K be algebraic closure of K. Okay, so that every polynomial over K is split into linear factor in E. Okay, the algebraic closure be an algebraic closure of K containing L. Then because G and now G and H also splits into linear factor. Okay, because E is also algebraic closure of K. Okay, so because pi is splits into linear factors, G and H also, the roots of G and H, they're just roots of pi also. So that's why. So G and H both splits into linear factors in E. Now take this, let alpha, yeah, alpha be a root of G and beta a root of H in E. Okay, we have such roots. Then, okay, first of all the roots of G and all the roots of H, they are distinct. They have no common factor. Okay, uh, is that the case? Otherwise, what G and H will be not co-prime. Okay. Oh, oh, sorry. No, no, that is not the case. G and H splits into linear factor. There may be G and H could be same also, right? They're just irreducible in index. We don't know if they're distinct or not. Yeah. Okay. Anyway, so let's see. So, okay. So here, G and H both splits into linear factors inside E, and alpha B roots of G and beta is the root of H inside E. Then, in fact, alpha and beta are also root of alpha beta are roots of pi also, in fact. So this is the case. Now, if we consider some automorphism of E, right, which permutes these roots, means, okay, what I want to say is that take some pi, okay, since pi is irreducible in kx, and since pi is irreducible for any sigma belonging to K algebra automorphism of E over K, sigma permutes the roots of pi. Sigma permutes the roots of pi. Okay, so in particularly, there exist. Okay, not permute. Let simply pi be our K algebra automorphism of E such that phi of phi of A, sorry, my phi and pi are getting mixed. Phi of A is equal to, sorry, phi of alpha is equal to beta. Okay, let phi be such an automorphism of E which sends alpha to beta. Then, okay, anything else? Yeah, phi b k algebra automorphism which sends alpha to beta. Now, what else? I want to restrict this phi to E. Phi, is this possible or not? Okay, first claim is that claim phi, this phi is phi of L, which is inside E, is contained in L. Okay, then I can restrict our phi to L. Okay, then this will be the automorphism of L, which will be working as sending H to G. Okay, then first of all, let me show this part. Okay, assume X belonging to phi L or T, some other name we should do. I'm going to prove this claim. Let T belongs to phi L Okay, what else is given? Phi is a K algebra automorphism. Okay, and we are looking image into image of L. So what is L? So let's see here. L is normal field extension. What we know is that this works. Okay, it works for normal extensions. So T belonging to phi of L. So T is equal to phi of some x, or no, some s, where s belongs to L. Okay, so but when s belongs to L, then we consider mu s k minimal polynomial for s in k with coefficient k. Consider this polynomial which is irreducible by default. Irreducible. So sigma. Okay, this phi permutes the roots of s. So then is phi is k algebra automorphism. K algebra homomorphism, in fact, homomorphism permutes the roots of mu sk and all the roots of mu sk belongs to belong to L. This is because L over K is normal and S belongs to L. So all the roots of mu sk, this implies that phi of S, which is a root of which is a root of mu sk belong to L. So this implies T belongs to S. So this is the case. So now we restrict. So we can restrict our domain of phi to L, which is also a field. So phi is a field homomorphism. Phi is in fact automorphism of field. Okay. So we are assuming L is finite dimensional. Finite field extensions are anyway injective homomorphism. So over K, if L has finite dimension, then injective vector space homomorphism, they are also subject to L to L. Okay, so phi is automorphism in that sense. So I'm not sure if it is finite extension L over K. If it is finite, then it works. Otherwise, still we can restrict our domain of phi. Okay, so code it is surjective anyway, right? Or it may not be. I don't know. So, but anyway, we can restrict our domain of phi to L, and then what we have, we are now worrying about this part, E over L. So what we have here, we know, we just know that uh, alpha goes to beta. Phi of alpha is equal to beta, and alpha is root of where alpha is a root of G, and beta is a root of H, and H is irreducible inside L. H is irreducible in Lx. This implies mu alpha L. This is just, sorry, this H is irreducible, then this will be mu L. H corresponds to beta. Okay, sorry. This is beta. So minimal irreducible polynomial. There I'm taking always monopolynomial, so don't worry about that. H is irreducible. This implies that, and beta satisfies that H. So minimal polynomial is exactly this irreducible polynomial H. Okay, and G is irreducible. This implies mu alpha L is equal to G. So alpha satisfies G, and G is irreducible also. So no minimal polynomial, means no minimal degree polynomial than G should be minimal polynomial for alpha. So it should be G only. Okay. So mu alpha L is equal to G. Now what we have here is that phi of alpha is equal to beta. So roots of mu alpha beta will go to, okay, applying phi. Now phi is L algebra homomorphism. L is fixed field, right? Phi of L is contained in L. This implies L is fixed by, yeah, L is fixed by phi. So this is, from the starting we can write something else. Let this notation. Phi restricts to L. So then we can, but phi is not fixing. Phi fixes L, but not elements of it, right? Phi fixes all the elements of K only, because phi is K algebra homomorphism. So phi sends one root of alpha to one. So what is happening here is that phi sends a root of h to a root of g. Okay, so goodbye. Uh, I'm thinking about that. Let me see what should pi sends the root of h to root of z. We should check that pi of h will itself go to pi of pi of h will be g. Okay, so this is what we wanted to show. There exists some pi. So this is what we wanted to show. We wanted to show there exists sigma belonging to odd L L over K. Oh, let me see what was the correct question. First of all, there exists sigma belonging to Galois L over K. Sigma of S is equal to G. Yeah, this is Galois L over K such that sigma of S is equal to G. Right. This is our question. So what we have seen here that one of the root of H is going to a root of G, or is it otherwise? Or so we have taken a normal extension phi be irreducible polynomial. Phi can be written as product of two irreducible since Lx. We have taken algebraic closure containing L. General both expressions to linear factors. Alpha be root of Z, beta be root of H. So okay, so here is little bit mistake. Okay, alpha beta be, are also roots of pi. Pi is irreducible in kx and sigma is K-algebra automorphism. Then sigma permutes roots of pi. Now, so let phi be K-algebra automorphism of phi such that phi of beta going to alpha. Okay, so that at the end we will say phi of s is equal to the automorphism of phi such that phi of beta is equal to alpha. Okay, then now we want to claim that phi restricts to L. So T be any element of phi L. So T can be written of this form. For some S where S belongs to L, we consider minimally reducible polynomial for S over K. Phi is K algebra homomorphism, so it permutes the roots of, because it is irreducible. This is what we have to remember. Okay, so it permutes root of mu sk. Then all the roots of mu sk belongs to L because L over K is normal and S belonging to L. One of the root belongs to there. So phi of S, which is also a root of mu sk, belongs to L. Now it is clear. Good. So T belongs to S. So we can restrict our domain of phi to L. So and phi of beta is equal to alpha, where alpha is root of g, beta is root of h. H is irreducible in Lx. This implies mu beta L is itself h. Yeah, this is correct. G is irreducible in Nx. This implies that mu alpha L is equal to g. This is also nice. So phi sends a root of g. Sorry, phi sends a root of h to root of g. Yeah, now it is correct. To a root of g. We wanted to show that there exists sigma in Galois L over k, that sigma of h is equal to g. So how should we say? We have just seen that one of the root of h is going to one of the root in g. So what we can say is just that phi restricting to L will be inside Galois group of L over K. Okay, because it just fixes elements of. Okay, wait a minute. I'm connecting my Bluetooth device. So what I wanted to say is this, that phi restricted to L belongs to Galois L over K. Okay. Now what? Let me write here all the details we have seen so far. P is L over K, and here over K, alpha beta belongs here, such that sig phi of beta is alpha. Okay, this is given. Yeah, this is given, and phi restricted to it. We want to. This is our claim. We can take sigma here. Take sigma is equal to phi. Okay. So what will happen? We want to show claim phi of h is equal to g. Okay. So this is your claim. What is happening here? Phi is, since alpha is a root of alpha. Sorry, beta. Beta is a root of h. So phi of beta, this is a root of phi of h. Okay. So this is kind of trivial if you see phi is an automorphism, K-algebra automorphism. Okay. Or it is not. Yeah, it is. Yeah, it is. It is always right in a equation where beta satisfies that equation. If you apply phi on it, because phi is homomorphism, in fact. So yeah, this is always the case. So if it was K-algebra automorphism phi, sorry, if this equation was with coefficients in K, then coefficients are fixed. So if alpha is a root of f, then phi of alpha is also root of f. We say like that because phi of f is same as phi of f is same as f. But here we are just writing phi of s, so it is no need to worry about it. So phi of yeah, after this phi of beta is equal to alpha. Alpha is so alpha is root of phi of h also as as well as a root of g. And since h is irreducible, phi of h will be irreducible. Okay, so phi of h is irreducible. It needs a verification kind of thing, but g is also irreducible. All this implies uh, mu alpha L, this is equal to G is equal to phi of S, uniqueness of minimal polynomial. Take after reducing, after dividing by a unit. So, okay, so sometimes irreducible polynomial we take uh, and 2 into that irreducible polynomial is also kind of irreducible. But we take monic polynomial, so in that if it is monic, then we don't need to write this. Let me. So h is anyway monic polynomial. Take if phi is monic, this implies h and g are monic. This will imply phi of h and g are monic. So no need to divide by any constant. So h is irreducible, hence phi s will be irreducible. So this implication I'm leaving an exercise, or it might not be true. I need to verify. Then if it is the case, then we have shown this g is equal to phi s because g and since g and h both are minimal polynomial for. Okay, so that this would be unique. So this is done last this week. We'll see next week. Okay, so I hope you're having good time with these exercises. I was little bit sleepy, so there might be some mistakes. If you find out, please write into this comment box. I will I will look into it. Okay, and I will reply for that. So okay, see you next week.